Welcome to my class. This is the first chapter of the General Relativity. Here is a question. How can we describe the mass of a liter water? We must first establish a unit that corresponds to the object described, with the only difference being a matter of scale. Based on this, we can derive this number and define it as the mass of this glass of water. Moreover, we not only use kilograms to describe mass, but also grams, pounds, and so on. Use grams to describe the mass of water is 8,000. Use pounds to describe the mass of water is 17.6. Although the units used to describe this glass of water are different, their three units all represent the same quantity, the mass of 8 liters of water. Therefore, we expect that there exists a conservation system among their three different units. We abstract this behavior and refer to it as transformation A. We then represent this process in a mathematical form, providing a precise and formula description of the transformation. So, what is the significance of this transformation A? It is evidently a constant number. The value of this constant A is easy to determine. We simply need to use a balance to measure how many grams are equivalent to 1 kilogram. Here, the value of A is clearly obtained. It is 1000. Thus, transformation A is determined through a comparison of physical objects. Clearly, A does not depend on the actual mass of the object. It only depends on the definition of the two different units. No matter how many liters of water are considered, the transformation between kilograms and grams consistently follows this formula. However, transformation A always have a directional property. This is normal. This kind of directional property changes when converting from grams to kilograms. We naturally want to understand how the inverse transformation is realized from kilograms to grams. Therefore, if we apply transformation A to cover a quantity from y to x, and then apply the inverse transformation A squared negative 1 to the result, we will find that it returns to y. We have not performed any actual transformation on y. This means that in the transformation process, y returns to itself. The mathematical number that leaves any quantity unchanged when multiplied is evidently 1. Accordingly, 1 serves as our unit conversion factor. Any unit, when transformed by the unit conversion factor, remains unchanged. Now the definition of the inverse transformation is evident. When multiplied by A, this composite mapping represents a unit conversion. Following, we are going to promote this rule to vector. We begin with a two-dimensional plane. We know that in any plane, two unit vectors are required to represent a vector. When we have these two unit vectors, any vector in this plane can be expressed as a combination of them. It can be written as P equal to x sub 1 times vector g sub negative 1 plus x sub 2 times vector g sub negative 2. The coefficients of unit vector x sub 1 and x sub 2 are coordinate components. If the base vectors in another coordinate system are analogous to g sub 1 and g sub 2, which are mutually perpendicular, then this coordinate system is called a Cartesian coordinate system. There are occasions where special coordinate systems are encountered. Such coordinate systems may have acids of unequal length and acids that are not orthogonal. Although we mostly use the Cartesian coordinate system compared to another systems, nonetheless, even in their coordinate systems, another vector can be resolved in two separate components. Similarly, this resembles the previous course where a single object's mass was described using two different units. Under their circumstance, a single vector can be represented in two distinct reference frames, similar to how the mass of a single object can be expressed using two different units. We expect that a transformation system exists between their two different reference frames. We now begin with the base vectors. F sub 1 and F sub 2 can both be expressed in terms of G sub 1 and G sub 2. We can also obtain the values of A sub 1 1, A sub 2 1, A sub 1 2, and A sub 2 2 through geometric construction. We incorporate the relationship obtained by decomposing one set of base vectors with respect to another into the component expression. Now we can derive the transformation relation between the components of y and x. Moreover, their relationship constitutes a system of linear equations. The four constants A sub 1 1 through A sub 2 2 in their equation do not depend on the specific values of x or y. Instead, they depend on the base vectors of the two coordinate systems. Now we extract their four numbers. We extract and progress their four numbers and then arrange them into an array. This array forms a matrix, which is denoted by the uppercase letter A. From this, we can see that the matrix represents a transformation from one coordinate system to another. Next, I will express the vectors x and y into the form of column vectors. Thus, the system of equations becomes a single equation. Since this equation is equivalent to the original system, it follows that we obtain the rule for matrix vector multiplication. By multiplying each element of a row of the left-hand matrix with the corresponding element of the right-hand column vector and summing the products, we obtain one component of the transformed vector. Let A be the matrix that transfers y to x. Then the transformation from x to y is represented by the inverse matrix A squared negative 1. Their product is the composite matrix, which is identity matrix that leaves everything unchanged. The product of their matrices is the composite matrix, namely the identity matrix, which produces no change. It is clearly that the identity matrix has ones on its diagonal and zero elsewhere. With only a few single calculations we can obtain it, and we denote this matrix by E. This set of operations applies not only to two-dimensional vectors, but to vectors of all dimensions. One only needs to extend the rows and columns in a straightforward manner. However, we also observe that as dimensional ability increases, explicitly writing out each transformation becomes increasingly cumbersome. Even in 3 dimensions, explaining it is already very cumbersome. Not to mention the case when we must handle 4-dimensional space-time. Accordingly, in the following lecture, we will present a highly significant technique for index simplification. Please look forward to it.